In this episode, we are taking on one of the most important ideas in application security because it helps explain how a seemingly ordinary input field can become the starting point for a serious breach. Injection flaws sound technical at first, but the core concept is actually simple enough for a new learner to understand clearly. A system is supposed to treat what a user provides as data, yet sometimes it accidentally treats that same input as part of a command, a query, or an instruction. When that confusion happens, the application may end up doing something the designer never intended, and that is where the danger begins. This matters so much in security work because many modern systems constantly accept input from users, other applications, devices, forms, search boxes, web requests, and background integrations. If even one part of that process is handled carelessly, an attacker may be able to influence what the system does behind the scenes. That is why injection flaws remain a foundational topic for security analysts, defenders, and anyone trying to understand how software can fail in ways that go far beyond a simple bug. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. At the most basic level, an injection flaw happens when untrusted input is mixed into a command or query in an unsafe way. The application expects information from a user, but instead of keeping that information separate from system instructions, it blends the two together. Once that boundary is blurred, the program may interpret part of the input as something to execute rather than something to store, search, or display. You can think of it like a receptionist who is supposed to write down a visitor's name, but instead mistakes part of the visitor's sentence as a direct order to unlock a door or delete a record. The problem is not that the system accepts input, because every useful application needs to do that. The problem is that the system fails to maintain a clean separation between content and control. This is why injection flaws are so serious. They do not just cause bad formatting or a small data error. They can alter behavior, expose information, bypass checks, or even change what happens on the server, depending on how much influence the attacker gains. To understand why this occurs, it helps to picture how applications work behind the scenes when they receive information from users. A person types something into a field, clicks a button, or sends a request through an interface, and the application then passes that input through layers of logic to perform a task. Sometimes the program checks a database, sometimes it searches logs, sometimes it asks the operating system to perform a function, and sometimes it interacts with another service. The risk appears when developers build those actions by stitching together user input and system instructions as one combined string rather than keeping them safely separated. Once that happens, the system may not know where the real command ends and where the user data begins. A careful attacker looks for exactly that weakness. They are not always trying to break the software with noise and chaos. Often they are testing whether the application will let them reshape a legitimate request into something far more powerful. That is why injection is really about trust boundaries, interpretation, and the danger of allowing outside input to control internal behavior. One of the most familiar examples is structured query language, SQL, injection, which targets the way an application talks to a database. Many systems rely on databases to store customer records, login details, inventory, case files, payment history, or other valuable information. If the application creates a database query by directly joining user input to the query text, an attacker may be able to change what the query means. Instead of asking for one expected record, the application might be tricked into returning more data than intended, changing data it should not change, or ignoring parts of a security check. The important idea for a beginner is not memorizing syntax or attack strings. The important idea is recognizing that the application is asking a database to do something, and unsafe input handling may let the attacker influence that request in ways the developer did not intend. That turns a normal search box, login field, or filter tool into a potential gateway for data exposure, corruption, or unauthorized access, all because the application failed to separate data from the database instruction itself. Injection is broader than databases. which is why learners should not reduce the topic to one famous example and stop there. Similar weaknesses can affect operating system commands, directory lookups, query languages, template engines, interpreters, and other components that process structured instructions. In each case, the core problem stays the same even if the technical details change. The system is meant to handle outside input as content, but it accidentally gives that input too much authority over what happens next. When the target is the operating system, the risk can be especially severe because the application may pass unsafe input into a shell or service that performs powerful actions on the host. When the target is a data store or service query, the attacker may gain visibility into information they were never meant to see. When the target is another interpreter, the attacker may manipulate application logic in unexpected ways. Security analysts therefore need to think in patterns rather than labels. If a component interprets commands or structured expressions, and if user input reaches that component unsafely, there is a meaningful chance that an injection flaw could exist. The reason injection flaws matter so much is that they can lead to several different outcomes, all of which are serious in different ways. In some cases, the attacker is after confidentiality, meaning they want to read records, messages, credentials, or internal data that should remain private. In other cases, the goal is integrity, where the attacker wants to alter stored information, tamper with application behavior, or insert false records that change business operations. Some attacks affect availability by causing errors, overloading a service, or breaking a critical workflow. There are also situations where injection becomes the first step in a larger compromise, allowing the attacker to learn more about the environment, bypass a security check, or pivot toward more valuable systems. This is why defenders should never think of injection as just a web developer's mistake. It can quickly become a business issue, a legal issue, a privacy issue, and a trust issue. A flaw that begins in one form field may end with damaged data, stolen customer information, or a major incident investigation involving multiple teams across the organization. A common misconception among beginners is that injection flaws only exist when a system crashes or behaves dramatically. In reality, a vulnerable application may continue working normally from the user's point of view while quietly giving away too much information or accepting harmful instructions. Another misunderstanding is that only old, sloppy, or obviously poorly written applications are at risk. Modern frameworks and tools can reduce the danger, but they do not remove it automatically if developers bypass safe patterns, mix trusted and untrusted data carelessly, or make risky assumptions about input. Some people also believe that filtering for a few suspicious characters is enough to solve the problem. That approach may catch simple cases, but it often fails because attackers adapt, encoding changes occur, and different backend components interpret data in different ways. Good defense comes from designing the interaction safely in the first place, not from hoping a short blacklist will stop every trick. That distinction matters because injection flaws are usually symptoms of deeper design and coding mistakes, not just the presence of a few strange characters in an input field. Input validation is part of the defensive conversation, but it is often misunderstood, so it is worth treating carefully. Validation means checking whether incoming data matches what the application legitimately expects, such as a date, an account number format, a product code, or a short search term. This helps reduce nonsense input and can stop some accidental or malicious misuse. However, validation alone is not the full answer to injection because even acceptable-looking input can still become dangerous if the application later mixes it unsafely into a command or query. A person can provide something that seems normal on the surface, yet the downstream system may interpret it in harmful ways if developers did not build the connection correctly. This is why validation should be paired with safer programming practices that preserve the separation between data and instructions all the way through processing. For a beginner, the main point is that validation is helpful, but it is not magic. It improves quality and reduces risk, yet it must work alongside stronger protections that ensure user input remains data at every stage rather than becoming part of executable logic. One of the strongest concepts to understand here is parameterization, even if you are not writing code yourself. Parameterization is a safer design approach in which the application sends the structure of a query or command separately from the data values that fill it. In simple terms, The system says this is the instruction, and this is the user-supplied content, and the two should never be confused. That clear boundary helps prevent the backend component from reinterpreting user input as control logic. The user's data is still accepted and processed, but it is handled in a way that limits its power to alter the meaning of the instruction. For analysts, this concept matters because it explains why some findings are much more dangerous than others. If a sensitive function is built through unsafe string construction, the risk can be high even before anyone proves full exploitation. If safer mechanisms are used consistently, the attack surface may be significantly reduced. You do not need to be a developer to appreciate the value of that distinction. It is enough to understand that safer design choices can prevent whole categories of problems rather than merely reacting after an issue appears. The environment around the application also shapes how severe an injection flaw becomes. A vulnerable application that runs with broad permissions, deep database access, or powerful service privileges gives an attacker more room to cause damage. By contrast, if the application has tightly limited access, segmented responsibilities, and narrow permissions, the impact may be contained even if a flaw exists. This is where broader security architecture intersects with software weakness. Least privilege, strong segmentation, careful service account design, and monitored access patterns can all reduce the blast radius of a mistake. None of those measures excuse the vulnerability, but they can make the difference between a limited incident and a major organizational crisis. Analysts need to think this way because a finding is not just about whether a flaw exists in isolation. It is also about what that flaw can touch, what trust relationships surround it, and whether the compromised component sits near valuable data or critical business functions. Injection flaws become especially dangerous when unsafe input handling is paired with excessive backend power. Detection can be challenging because injection flaws do not always announce themselves loudly. Some attacks generate obvious application errors, but others succeed quietly and leave only subtle clues in logs or user activity. Security teams may notice repeated unusual requests, unexpected database behavior, odd error patterns, abnormal search activity, sudden spikes in failed transactions, or access to records that do not match the user's normal scope. Application logs, web server logs, database monitoring, and behavioral analytics can all contribute useful clues, but defenders still need context to interpret what they are seeing. A strange request alone may not prove exploitation, and a clean-looking log does not guarantee safety if the visibility is weak. That is why monitoring should be paired with secure development, careful testing, and thoughtful review rather than treated as a replacement for prevention. Once an attacker successfully exploits an injection flaw, the damage may already be underway before the organization notices anything unusual. Good detection matters, but preventing unsafe input handling in the first place remains the stronger long-term defense. When security teams assess injection-related risk, they need to consider both the likelihood of exploitation and the consequences if exploitation occurs. A flaw in a low-value internal tool with limited permissions still matters, but it may not demand the same immediate response as a flaw touching customer records, identity systems, financial data, or internet-facing business applications. Analysts should ask what kind of interpreter or query engine is involved, what data or actions are accessible through it, how exposed the vulnerable path is, and whether existing controls reduce or magnify the damage. They should also think about whether the flaw could support chaining with other weaknesses. A modest injection issue might become much more serious if it enables bypass of authentication checks, exposure of secrets, or movement into a more privileged area of the environment. This style of analysis is what makes vulnerability management meaningful. It is not just about labeling a flaw and assigning a number. It is about understanding how technical weakness, business importance, access level, and attacker opportunity combine into real-world risk. It is helpful to remember that injection flaws often reflect organizational habits rather than one isolated coding error. Development speed, poor review practices, unclear secure coding standards, inconsistent testing, and pressure to ship features quickly can all contribute to the same category of weakness appearing in different parts of an environment. One team may fix a visible issue in a public-facing form, while similar unsafe patterns remain hidden in internal tools, reporting functions, batch jobs, or service integrations. That means mature defense requires more than a one-time patch. It requires better development discipline, safer defaults, awareness of dangerous patterns, and processes that encourage teams to ask not just whether the software works, but whether it interprets user-controlled data safely at every trust boundary. For a beginner, this is a useful mindset because cybersecurity is rarely about dramatic one-off mistakes alone. It is often about repeated patterns that emerge when convenience, speed, and weak guardrails gradually shape how systems are built. Injection flaws fit that pattern very well, which is why they remain such an important topic to understand. By the time you step back and look at the whole picture, injection flaws become much easier to explain in plain language. They happen when a system fails to keep outside input in its proper place and instead allows that input to influence commands, queries, or instructions behind the scenes. The result may be unauthorized access, altered data, disrupted operations, or a foothold for deeper compromise, all from what began as ordinary interaction with an application. The strongest takeaway is that security here depends on boundaries. Data must stay data, instructions must stay instructions, and the application must never blur the line between the two just because it is trying to be flexible or convenient. Once you understand that principle, the topic stops feeling mysterious and starts feeling practical. You can evaluate systems more clearly, ask better questions during analysis, and recognize why secure input handling is not a niche developer concern, but a central part of defending modern organizations. That is the real lesson behind injection flaws, and it is why this topic remains so important for anyone building or protecting software.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.